Okay, folks, so we were talking about molecules and other things that have handedness, left-handed or right-handed, a property called chirality, and that's ubiquitous in nature. Ubiquitous, what's that mean again? Common, found all over the place. So if you go catch crab, if you're catching crabs to eat or something, a lot of times they get one claw is bigger than the other, and some animals have twists to their tusks or horns. And is it a left-handed threaded screw or right-handed? So it varies. So what about life off the Earth? I'm kind of curious. Exoplanets. Well, this one, if that's Earth, that looks like Earth. This one's going to have a way heavy gravity. You're going to get crushed. Oh, I get so tired just walking up the stairs. So what about that? We've found lots of these in your guys' lifetimes. We've found more Earths than at any time before you guys were alive. Think about that. Any questions before we launch into outer space? Is everyone at least 15 years old, or what? I don't know. What's the age limit for going to outer space? Fasten your seatbelts.
My name is John Cefalu, and I'm the CEO of the...
That's got to pay the price. Incidentally, if anyone ever finds any of my talks with ads on it, please let me know. They're not supposed to be ads on any of my talks. Someone had gone in and monetized some, and I caught and got rid of some of that, but please let me know. Oh, heavens, this is really long, so we'll just take a squint at it.
Billions of planets caught up in the vast whirlpool of the Milky Way galaxy. From Earth, a lonely outpost floating on one of its spiral arms, humans have begun to peer across the void. And just recently, scientists have found the first Earth-sized habitable zone world. NASA's exoplanet program was created to find unmistakable signs of life on other planets.
Habitable. I would say most English speakers, he sounds a bit like a Brit or something, I'm not quite sure. Habitable, ability to inhabit, so habitable. Usually that means liquid water. Habitable or habitable. Okay, that's what he meant.
During the search for extraterrestrial life and Earth-like planets, NASA has found some incredibly bizarre alien worlds. We'll talk briefly about the planet's host star and the discovered Earth-like planets themselves. PSR J1719-1438 is probably one of the most fantastical cosmic objects you'll learn about here. The first thing to know is that 1438 is a neutron star, a small but incredibly dense stellar object which usually averages no more than 12 miles in diameter. Neutron stars are so dense that just 1 teaspoon of their stellar material would weigh about 1 billion tons on Earth.
Whoa, just hold the phone right there. And there's a little reason for that, and it's real simple. And you guys know enough chemistry to see that. 1 billion tons a teaspoon, I think is what he said. I'm just gonna switch screens here real quick, because it's a long show. I didn't realize it's so long. But we know the basic structure of an atom. Okay, on screen. So what's in the chewy center? So let's say it's a hydrogen atom, then there'd just be a proton in there. So remember this distance here, oops, okay, gotta scan out a little bit. So we could have 1 electron and just 1 proton, or we could have, that would be hydrogen, or what if we have 2 protons and 2 neutrons? And then we have to have 2 electrons, and that would be helium. the second most abundant. So it turns out that the nucleus here, that's that inner part there, oops, the nucleus is really tiny. So this is, just gonna pull it up on Wiki real quick. It's super tiny, but almost, let's see, like 99% of the mass, about 99.9% of the mass is in the nucleus. So that means the electrons are just like 0.1% of the mass. But what about the size, the volume? So I'm just going to pull up real quick, little wiki, and look at an atom. And we'll get some real numbers here. Okay, I'm going to switch screens. So I just typed in atom into Wiki, and it has these prefixes here. Okay, so this is femtometer. We started out the semester I asked you guys to note these Greek prefixes, milli, kilo, milli is 1,000th, kilo is 1,000, kilogram, kilometer. And here 99.94% of the atom's mass is in the nucleus. So I was pretty close with 99.9. But what about the diameter? Okay, so it shows here that looks like the diameter is femtometer, 1 femtometer. So I'll jot that down. 1 FM. And this is 100 picometers. So this bar, let's just say it's roughly the diameter of the atom. So about 100 picometer. And then all we have to do is a little arithmetic, and it's not that hard. So the volume, it goes up as the cube of the diameter or the radius. So let's just look at a few numbers here. Do some arithmetic. Okay, come on, focus. Okay, so our nucleus is just protons and neutrons, and that's about 99.9% of the mass is in the nucleus. And it was 1 femtometer. And we'll call the diameter about 100 picometers. Okay, so I'm going to simplify that now. Here's my atom. Okay, and we'll say that's 1 femtometer, and this was 100 picometers. Okay, that's atom. So that's, what was the F again? 1 times 10 to the what power? Minus, they both start with the letter F, 15 meters. And this is 100, and P is 10 to the minus 12 meters. Okay, so this is 10 to the second power times 10 to the minus 12th, and we add exponents, that equals 10 to the minus 10 of a meter. Okay, so when you multiply, this 100 is 10 to the second power, and that's times, and that's what this means. 100 times, that's pico, 10 to the minus 12. So you just add the exponents when multiplying. So a plus 2 and a minus 12 is minus 10. And here we have 10 to the minus 15. Wow. So how many times bigger is this? 10 to the 5 So the difference between this and this is a factor of 10 to the 5. That's 100, 1 followed by 5 zeros. 1, 2, 3, 4, 5 zeros. 100,000 times. Okay, you could say the nucleus is 100,000 times smaller, or the atom is 100,000 times bigger than the nucleus. So what part of the volume? Okay, maybe you guys are going to start crying, but volume of a sphere equals 4/3 pi r cubed. So r is d over 2. So this is diameter. So radius is 1/2 of diameter. So let's just calculate the volume real quick. 4/3 pi, and we'll just say 0.5 times 10 to the, we'll do the nucleus first, and atom. 10 to the minus 15. But remember, we cubed that thing. And leave some space. So this is just amazing. You won't believe this. Okay. 0.5. 0.5. And an exponent 15, change signs. And I want to cube that guy. And I need stronger glasses. So I don't have a cube button, so I can do my X to the Y button. That's this one. So I press this and put to the 3rd power. Goes that. And see, times pi, which is here, times 4 divided by 3 equals 10 to the minus 45 cubic meters. Okay, so we'll do the same thing for the atom. It's 4/3 pi and 10 to the minus 10, so 0.5 times 10 to the minus 10, and we've got to cube that puppy. And so this is just ballpark. Okay. So 0.5, and our exponent 10, change sign, and then I want to cube it. So, oops, you can see this button here. So I have my number in there, 0.5 times exponent 10 to the minus 10 minus, and then I want to cube it. So I hit this button, that button, and that button. And then I go times 4, divide by 3. And I get 1.7 times 10 to the minus 31. So now I'm going to divide that by the size of the nucleus. Okay, so this divided by nuclear volume, that's this number here. So 1.7 times 10 to the 14 times bigger. So that's how much bigger the atom is than the nucleus. So if I want to find the reciprocal of that, the nucleus divided by the atom, I just do the 1/x button, which is right there. And I get 6 times 10 to the minus 15 nucleus volume as part of atom. So, okay, there's the math, just to remind you, we can do some math. You should be able to work out some of that. One at this level, I would probably make extra credit. But basically, almost all of the volume, let's see, the volume is about 1.7 times volume of atom, 10 to the 14. So let's see. So that's 10 to the 14s. We could break that down. That's a billion. And then we got 5 left. 100,000. So it's about 200,000 billion times the volume of the nucleus. So if we shrink that down on a neutron star, you basically shrink. So no electron space. They collapse to nuclear volume. So all the mass gets smaller by that much. That's just a huge amount. Okay. So that's what they were talking about. Come on, we can do this. Okay, back to the movies. 1 billion tons for a teaspoon. That's how that worked, because the electrons collapse down to the nucleus on the atom. And all the mass is still there. None of the mass went away. There's just so much pressure that it just collapses.
It's also a pulsar, which is a neutron star that emits strong beams of electromagnetic radiation from its magnetic poles and has intense magnetic fields, about 1 trillion times stronger than Earth's magnetic field. Some pulsars have an amazingly fast rotational spin.
Well, that's a lot of... Let's see if we can find some friendlier ones. A shorter one with life. Let's see. Exoplanet Goldilocks. So why Goldilocks? The Goldilocks zone. Okay, here's a young lady, better looking than I am, and she's going to talk to us about NASA hunting for planets in the Goldilocks zone.
Facebook connects people. It's what we do.
The hunt for exoplanets. Planets just like ours, orbiting stars in a different solar system. Where are they hiding? Can they support life? And when exactly can we move there? Because we've screwed up this planet and I want to leave. I'm Claire Riley. Welcome to Watch This Space. From the CNET studios in Sydney, this is your weekly guide to everything on Earth you need to know about space. And tonight, we're all alone in the universe. Or are we? Well, probably, but maybe not. That's right, we're on the hunt for exoplanets, and we're not going to stop looking under the giant intergalactic couch till we've found all of them. Exoplanets are like regular planets, but they exist outside our solar system, orbiting around their own stars. They're also called extrasolar planets, because just like your friend who turns up to every birthday party in a different Lurex jumpsuit, they're just a little bit extra. We've known about exoplanets for decades, and we had our first confirmed discovery of one in 1995. Since then, our exoplanet hunt has been going off like a frog in a sock. According to NASA, we've had more than 3,700 confirmed discoveries of exoplanets in just a couple of decades, with a further 2,900 potential candidate planets that are still unconfirmed. They could...
Just wanted to pause on that. They found thousands of planets in the last couple of decades. That's about the lifespan of the average university student, couple of decades. And geez, in the decades before that, you know, when I was a kid, they didn't know of any. None. When I was at university for the first time, they didn't know of any exoplanets that were at all Earth-like. So that's just a lot. Go and back it up just a bit. 3,700 since around the time you guys were born. That's a lot. But don't hold your breath. They're not available. So we got to deal with this one and fix this one.
Of exoplanets in just a couple of decades, with a further 2,900 potential candidate planets that are still unconfirmed. They could be a good match, but scientists still haven't swiped right on them yet. In total, we've discovered more than 2,800 planetary systems, stars that have their own planets just hanging out nearby. Just like the planets in our own solar system, they're all really different. Some of them might have rings, like Saturn, others could have water. Some of them are massive, and some are close in size to Earth. And then there's planets like HD 189733b, where it rains glass sideways, and which Wikipedia has called a hot Jupiter with poor prospects for extraterrestrial life. That's right, the popular girl at your Halloween party isn't the only one trying to be a hot Jupiter this year. And speaking of HD 189733b, let's talk about those names. Exoplanet names sound like they're pulled from the world's most boring index card catalogue, or from your uncle's Star Trek fanfic. Yeah, I'm looking at you, Draugr. So why the weird names? Well, because if we left it to an internet vote, the public would probably try to name them all Pluto McPlutoface or Mr. Starry Pants. So the International Astronomical Union has created a naming convention to help sort those thousands of exoplanets out. Some are named after their star, like 51 Pegasi b, or the astronomer that catalogued them, like Lisa 581, named...
Okay, so I'm going to switch it up a little here, and I know that folks want to know, we got a test coming up next time on Wednesday, so what's going to be on the test and where's the study guide? So here's where you can look for starting study guide. I mean, it's of course coming to class and taking notes, and when I say write this down, this word might be on the test, that's a hint. But here we go, looking in our chats here. So pop and open the chats since the last test, which was, let's see, when was the last test? The next one is on Wednesday. And I just wrote it down. Oh, one before that was March 2nd. So after March 2nd. So these March 9, March 2nd. So I think that would be maybe after the test, or that'd be the earliest one. But here what I'm showing you is... And then after you have, I've given you a few minutes to read that announcement. Oh, sorry, that's me. Okay, what I do is talking. So here's what a lot of you folks look like. There's me. And here's what I get to see when I give a talk. So it's kind of one-sided relationship. Okay, so... may not post. So some of these here, not this one obviously, have information about the talk. So let's kill this one off and go back to here. And let's pop open this next one here. Okay, so here, there's this show more stuff, show less and show more. So as I start off, often asking if there are any questions, and then did a review of test 2 calculations, asked for questions, discussed what's on tests, screenshots, you know, if you have some problem. And then we stopped that and went on to some YouTube chats. Okay, so this is a little synopsis, a little summary that on some of these, it's more complete than others. But this is March 9, that's fair game for the next test since the previous one test was March 2. So this one reviews the first test. So then going back to the March 9B, okay, there are a couple of tricks that I'm showing you here. One is go down to the description, and where it says show more, show more. One-way conversation. Okay. All right. So on this one, there's not a lot of description, but remember I showed you this one trick here where you can go into this. Read it faster than you can read it. And that's a trick that I'm just telling you about. You can go to where the settings is here, and you can adjust the playback speed, and you can make it faster than normal. And that way you don't need to take as long to listen to the talk. What happened? What's the chemistry here? Here's the candle. The wax is being melted and burned, and then vapors are going up, and he blows out the flame, and he lights it well above the wick, and the flame propagates down. How could that be? What must there be in the air in order for the flame to move downward? Like combustible gases. Be a good bet. Okay, so what I'm showing you here is how you can review. All right, let's have a look at this next one here. So what are the tricks? You go down to the show more, gases and exponential growth. So we did a few little gas calculations, and I could show you one more if you like in the remaining 4 minutes of class today. And growth, exponential growth and decay. Remember our magic formula, 70 divided by percent equals either the doubling time or the half-life. And we repeated that a number of times. So here on the next one, you can just pause it and, okay, again, doubling times and half times. Okay, and then last time or so, a few times ago, spider silk, stronger than steel, and zero population growth again. Oh, and world population growth, we looked at it. And then we looked at deep time. Overview of YouTubes we watched last time. So that's what you guys look like. This is pretty cool. Thank you. Okay, guys, it's Wednesday. All right. And then the most recent one, I think. Okay, that breaks it up nicely. So we watched a few videos last time, and we looked at molecular machines within us. Oh, that's supposed to be an R there. And the T is right next to the R on the keyboard. Continental drift, like plate tectonics, and possible hugeness of deep time. Carl Sagan and others on the Drake equation, the way to estimate just ballpark if there's extra intelligent life off the Earth. We still wonder if there's intelligent life on the Earth. I hear you cry, looking at world news. So those are your tricks for things. And I invite you all, as always, to write test questions yourself. If they're reasonable test questions, you know, multiple choice is good. Even matching or something. I might just use them on the test. And if you wrote them, you'll probably know the answers. Okay, so what about that? Any questions? These were a few of our vocabulary words today. Gyral means comes in lefties and righties. Racemic, 50-50 mix of lefties and righties. Abiotic, made without life or just without life. Abiogenesis means made without life. That's a little ditto of what's above there. In life on Earth, we have L amino acids and D sugars by and large. So if it's all left or all right, we can call that optically pure. And with life, you typically get all one or all the other. And here's the little diagram of why they call it optically pure. So you take some pure sugar water, D sugar, put it in, it rotates plane polarized light. And we looked at just a little simple arithmetic and some prefixes, remembering that pico equals 10 to the minus 12 Pikachu. And femto is 10 to the minus 15. And did a little arithmetic and found out that the volume of an atom is huge. The nucleus is hardly any of the volume. It's 1 divided by this number. And yet, what portion of the mass is in the nucleus? 99.9%, which I think we had on a previous test. And here's just the equation for the volume of a sphere, which maybe I'll throw in for extra credit. And if you got stuck and needed this equation on a test, you could just wiki it up. Okay. So help me write the test, you guys. Make it easier on yourselves and me too. And let me know if you have questions. But just like last time, part of the test will be online on La Lima, and it will open at least during class time. Probably pad it a little on each side. That's for the multiple choice. And then the short answer that you need to scan beautifully and turn in, I'll give you until, say, noon the next day. Usually it would be 5 p.m. that night, but since class is over by 4:15, and for some people it might be humbug to get to a printer or something, I'll make it noon the next day. Should give you plenty of time. And as always, for every test, as started the class, online courses, you need good internet access. You need a computer. Do not try to do it on your laptop or your phone or iPad. Sorry, laptop's fine. Don't try it on an iPad or a phone. And make sure you have good net connections. Drive to campus or somewhere equivalent if need be. Okay? If you guys write the test, easier for me and easier for you. So.
I'm sorry, Professor. When was the test again? What day?
Anyone want to help out with that?
Wednesday.
Okay.
Yep, coming right up. Just as planned. And as we go along, most of you have really gotten a taste of the math, the basic math, and it's just not going to get much, more than that. So we should be having more fun, watching more videos. So pick some out. Let me know what you want to talk about, what you want to watch. Okay? Overtime. So signing out, Captain Honolulu.